And maybe tell us a little bit about yourself. Kenneth.
Sure.
Because,
Yeah, because you guys don't know.
yeah.
So I'm a professor at the University of Central Florida, which you guys probably heard of. I work in, well, I'm in the computer science department, and I work in machine learning in particular, which is an area of artificial intelligence. And these are some of the interests I have, so neural networks and evolutionary computation. They're really specific. Some of you may not have heard of these, some of you probably have. So I do research in artificial intelligence. I think that Derek was initially interested in some neural network questions, and that's what we spoke about a lot when we met. But when I was thinking, so in terms of this talk, like what are we going to talk about for a talk? I thought it'd be more interesting, maybe more provocative and more fun to talk about our book, which is what you see to the left there. Yes, to your left there, which is about certain kinds of insights that we found through doing artificial intelligence experiments, but insights that have far wider implications than just artificial intelligence. So they apply to like anything you might possibly do. So what I hope to do then is to be able to give you a little bit of taste of AI for fun, because that's probably what I would be most expected to talk about, but also to give you this kind of larger perspective on the implications for how you do business and run your whole life. So that's what this book is about, and you'll see why that makes sense. It sounds a little crazy at first, but I'll make sense out of it. So what this says here is that we were researching artificial intelligence, and we ran into this flaw. We discovered it through experiments that we did on computers, which I'll show you, a flaw with objectives. It's a very general statement. It's interesting to think about because I think a lot of you have objectives, probably at work or in your life. And I'm telling you that there's a big problem when you have the objective. So it's something to think about. Now, so when we first noticed this, it was just in artificial intelligence experiments, but we realized that there's consequences now way outside of AI because of this. And this is very unusual. I mean, usually you don't do experiments with computers and suddenly realize you need to run your life in a different way. So this took a while to really pan out and be exposed, but ultimately we realized that there's something really significant going on. And so the main message here is that, what I'll show you, and I'll motivate this, is that objectives, or having an objective, like something you're trying to accomplish that's explicitly specified as an objective, can block its own achievement. And that makes having objectives an obstacle to creativity and innovation. So something that any industry that's aiming for some kind of innovation should be worried about, which is like almost every industry. And there's another caveat, which I'll get into a little, since it's just also interesting, which goes along with this, which is that's really important to protect individual autonomy and collaboration. When we collaborate with each other as human beings, can be dangerously objective or cause things to become more objective than they otherwise would be. So I think what I'll do, and along the way, I'm going to also show you a few examples of design-based AI as well, just because I think that's probably the most relevant stuff to this group that our work touches on. But the main story will be to start with the AI, show you these experiments, which are very unusual experiments, and then give you these kind of broader implications that I just outlined here. So here's the experiment. It's called Pick Reader. And as I say to people when I talk about this, this is, first this will seem really, really off topic, and you say, what does this have to do with anything? It's like a toy. But you'll see that it ties in very nicely to the point that I'm making. So what is going on here? What you're looking at is 15 separate images. Each one is being generated by a system called Pick Reader, and you can play this on the web. And what this system is set up to do is to allow you to breed pictures. So if you're familiar with breeding, like you can breed dogs or you can breed horses, and this is exactly the same principle, except that this is your population, these blobs, and you can breed them. So what does that actually mean? Well, it means like maybe I think this one's the best. This is subjective, so that's just my preference. Maybe I like those curves. So say, okay, now you have children. And now it's a parent, and there it's children. And these were generated by the system. I didn't know its children would look like this. These are its actual children. It had children. They're all slightly different, but many of them look very similar. One of them here has a mutation of some sort that's very noticeable. So I might say, okay, that's interesting. Let's see what happens if that one has children. So I pick that one, it has children, so there's children, and so on and so forth. And so you can just keep playing this game and you're breeding. And of course, what I showed you is asexual, but it doesn't really matter for these purposes because these aren't real animals. We can do sexual as well, but it really doesn't matter. So here's the question now. I mean, you've seen this little toy. I haven't really told you how it's generating these, but there's some artificial DNA under the hood. I'll give you a little more exposure to that momentarily. So they evolve like we do. I mean, when you have a child, it's not a clone of you, but it's somewhat related to you. So the question is, what do you think you could do if you played this game for a while? I don't know, several dozen clicks. Like, would these get better, or where do you think it could go? And the answer that we discovered, because we put this on the web, so like anybody could just use this, and we just see what happens. And actually, people can publish their discoveries back to the web. So this big collection started growing of stuff that was discovered through this evolutionary process. And so we got to see, like, where does this go? And we actually found this really surprising and actually, I think, amazing to see what kind of things people discovered. And so these are actual evolved images. There's no retouching. There's no artists involved in any of this. All of it is entirely bred from scratch from the blobs that you saw. And this is just a small sampling, so we have thousands of these kinds of things. Not everything that's published is great, but many of them are of this quality. Like, I mean, look, like this looks like a butterfly. There's a car. Actually has 2 wheels. Actually, Jupiter has its red spot, and so forth. And there's a pig. And so this is really, in some sense, remarkable when you consider, the modest origins of where this is coming from, this kind of blob. Okay, so I think the question then is like, what is actually happening here? And I want to show you that what's happening is really, really remarkable. Maybe more so than you might already think. Like how these discoveries are actually being made, because that's where the story gets quite interesting. And this is something that only we would be able to discover by actually having run this experiment, because otherwise we can't really say how discoveries would be made, but we actually have the full record of everything anybody ever did in the system. So we know everything about how this happened. And it turns out that the story is very, very surprising. So, yeah.
DTO? Oh, mine and Iran.
Okay, so what I want to do now is I'm going to give you a little technical detail. Most of the talk I'm not going to do this, but I figured you guys probably at a level where you want to know a little bit more under the hood. So I just want to tell you what is generating the pictures. Okay, so this is really the one technical slide that I'll do, just to maybe make people want to see some math or something to feel better. How are we generating these pictures? Well, what's going on is the pictures are really just a function, like a mathematical function that is taking in as input x and y. This is depicted as a graph, but it's really a function. This f depicts a function. So it takes in the inputs x and y, and that's why I have this xy plane up here. Because what it's going to do is it's going to pick a color for every xy coordinate. So basically I'm going to query the function with x comma y, and then whatever it outputs, which is a 3 variable vector, HSV, will be interpreted as a color. And then I'll just paint that color at that point. So what's happening is the function, which is the inside of this box, is what's evolving when you are asking for children. And so the function is just a composition of small, simple functions, which are always chosen from among those sets. It's a Gaussian, a sigmoid, a sine, and a linear. And that's what those look like. And then this graph represents the structure of their composition. So what this is saying is like, x feeds into this Gaussian, and its output then feeds into the sigmoid, and then its output feeds into that sigmoid, and eventually we get an output there. And the structure of this graph is what's evolving. So the structure means what are the nodes here, what are the connections among the nodes, and also something that you can't really see explicitly here is that the connections have weights. So it's like the output of the Gaussian is multiplied by a coefficient before it's fed into the sigmoid, and the coefficient we call a weight. So this actually looks a lot like a neural network. If anybody ever saw a neural network, it's almost exactly like a neural network. So you could even think of this as we're evolving a neural network that outputs a picture. If you know anything about neural networks, but you don't have to. But the one difference that you would notice is just that these internal functions are not the usual thing you would find in a neural network. So we changed the set of functions to our special set that we had reasons to believe would lead to good geometric properties. Well, as you can see, for example, Gaussian is symmetric, sine is a repeating pattern, so we thought we'll get geometric, we'll get symmetric patterns, we'll get repeating patterns, and so forth. We had a rationale behind this. But what's happening is, like, if you say you have a child, what happens is that this is the DNA of the parent, and then there'll be a mutation. So it might be like a new connection just appears, and that would be just a random mutation. Or maybe the weight here is perturbed by some random amount. So something random happens, and that's how children happen. And we call these CPPNs. This is this kind of mouthful term here, but it stands for Compositional Pattern Producing Network. That doesn't matter what we call them, really, just a terminology. But what's important is just to recognize that as mutations happen, sometimes they cause this network here to get bigger. And that means that the complexity of what they can represent is also growing. So that's why complexity can go up in the system. It's because the underlying DNA, so to speak, which is this, is getting bigger over time. And this did happen in nature, actually, our ancestors had many fewer genes than we have. And over time, there are certain things that happen sometimes that cause the number of genes to expand in biology. And so something similar is happening here and allowing this to get more complex. Again, I'm just giving you a sense of what's under the hood there. That does not explain how we got all this. In fact, it makes it even, I think, a little bit more perplexing because now you can think of it as, okay, you're in high school and your math teacher says, okay, give me the equation for a car. And this is an extremely hard problem. And the fact that people are finding things like that routinely is really surprising because under the hood there's just Gaussians and sigmoids and sines and so forth. So we want to know, how is this happening? Here's where I'm going to digress for 1 second because this is a design group. So like I said, I wanted to show you along the way a few design examples. So I'm digressing away from my main point just for a second just to show you some examples of other things that have been generated by evolving structures like this. We call this a CPPN, and here you're seeing it producing pictures. But it's also been used to produce 3D objects. This is called endless forms. So these are, you can think of almost like 3D pictures, but these are actually printed out on 3D printers and they come from the same system. It's been used to evolve creatures and their morphologies and their control apparatus. So more practical, some of these could be actually just built as robots. And it's been used in practical design. So here we see different types of mechanical structures. Like this is a vibrational design. And I'm not sure what this is for. It could do something. It's like some kind of truss structure. And so all of these things are being generated through the same process that generates these pictures. So basically the point is that the pictures, it's not clear what their utility is. They are going to teach us an important lesson. But you can also kind of think, and sort of interesting to consider, that the same kind of process and the same kind of underlying representation is able to produce all of this stuff without a human designer. So that's kind of interesting. Okay, back to pick breeder. So the question, though, that I want to sort of ask here, now that we've seen these discoveries, which are human-guided, but basically through breeding, is how it's happening. So return to that for a moment. And to begin to answer that question, first I want to tell you one other aspect of the system. So this is going to be a little puzzle that we're going to unpack, and it's quite interesting as we unpack it. This is like one of the more easy ingredients. So this is not going to give us the full explanation, but this is going to help us to understand. So I just want you to know this is happening. So it's something called branching. So what is branching? This is something you can do on this pick breeder site. So branching means that, like I said, people who discover things can publish them back to the site. Like there's a publish button. And when they do publish those images back to the site, other people who go browse the site, which could include you if you went there, can see the things that were discovered. And so the system is actually accumulating many examples over time. And these examples then can be what's called branched, which means I can ask to continue evolving from where someone else left off. And that's what I mean by branching. So in other words, somebody discovered this, it's kind of cartoon face, and so now it's on the site. So now somebody else can come in and say I want to branch from that. And then we can evolve that further. And so if you did that, you'd see an interface like this, which is basically the same interface. But now it's just, well, okay, we branched from that. So instead of starting from scratch, which are blobs, which we call starting from scratch, we're starting from something that was already discovered. And now, naturally, like the children or offspring will look somewhat similar, but not exactly the same, and we could play the same game. So I can say, okay, well, that's interesting. It kind of opened its mouth, so now make that apparent, and so forth. And now I can do my own session, and eventually, that button says publish, so I could then publish what I discovered back. And so what's happening is you're getting branches upon branches upon branches, which looks like this. So biologists would call this a phylogeny. But what's happening is like somebody discovers something, and then so all these other people say, oh, let's branch off that and see where we can go. And we accumulate more and more branching tree, which we could call a phylogeny. This phylogeny is a tiny subphylogeny of the entire system. Like I said, there's about 10,000 images that have been published. This is some small number of that, but it just shows you several users interacting with each other implicitly. So every single connection here is a session, like a session where one user just branched from something and on their own then got to the next thing. The length of the connections doesn't mean anything. So the session could be arbitrarily long or short, but each node represents a publication event. So we're seeing the branching of many users. There's about 30 users involved in this particular subphylogeny. So this is really what's going on. So like the things you see here are sort of at some depth in this tree of branching, people branching upon each other's stuff. Okay, but I still claim, and I'll support that is not sufficient to explain the miracle that's happening here and why these kinds of discoveries are being made. You can just see a little bit more of the diversity of stuff that's being discovered here, which I think is quite remarkable. Like if you just think about it, like stuff like, well, here's a handle on this picture. What are the chances that some random event will happen and just cause a handle to appear? How is this happening? How did we get a stem on this apple, which is asymmetric, and yet the apple is symmetric? I mean, what is the luck that's involved in this kind of thing? So over and over again, there's some kind of like amazing coincidences seem to be happening, but it's consistently happening. And so we need to explain why that is. And at this point, what I want to do is just to respond to one possible criticism of my point, which is if you don't really believe me that this is so amazing, there could be one reason for that, which I want to now knock down, which is, okay, here's the counter argument, why we shouldn't be amazed. Imagine that, like, I wanted to evolve like an apple. So I start from scratch, I just got blobs, so I want an apple. No problem. So I want to get an apple. And so maybe what I would say is, okay, there's just a bunch of blobs in front of me, but and none of them look like apples naturally, but one might look more like apples than the others. So I would choose that one naturally. So really what I'm talking about here is an objective. So I have an objective, which is the apple. It starts to fit into this framework that I was talking about at the beginning. And so now, okay, I picked the thing that looks the most like an apple. It has offspring. And they still don't look good like an apple, but they're a little more apple-like because I chose the most apple-like thing. So now I'll just choose from those the most apple-like thing. And then I'll do it again. And they have offspring, and I have a slightly more apple-like population, and I choose more. So you could imagine that, well, wouldn't we inevitably get an apple if we just play this long enough? And this is a metaphor for like the way we run society. Like we set objectives and then we measure progress towards the objective, and you're considered to be going in the right direction if your metric is going up. And so, like many people have been raised and taught to believe in this kind of this type of approach to design. But what's interesting here is that absolutely does not work at all. So that cannot be the explanation. And when I say it does not work at all, I mean in the system. So we have empirical evidence that does not work. So you can't do it that way. So what would actually happen is if you started out and said, I want an apple, and start comparing things to the apple, what you would find out is that you will eventually just get completely stuck on something that doesn't look anything like an apple, and you'll be extremely frustrated and not understand what's going on and never want to play again. And this happens over and over again because most people are objectively oriented and do want to play the game that way. The people who found these things were not looking for them. It's an important role, and we'll see why that is. Now, if that's confusing to you and you say, well, how can this possibly be? Like, that's the only rational way to approach, whatever. Well, if you think about it, this is obviously a complex space. Just like any design space that's worth anything, it has to be complex. Because the point here is that if something is so simple that you know how to get there, then there's no problem, right? So it can't actually be that interesting. So things that are worth doing in terms of innovation are always going to be things where we don't actually know the stepping stones that lead there. Or rather, the point is there are stepping stones on the road to something that we're trying to discover. We don't know what those stepping stones are, and it is often the case that the stepping stones are something that's surprising. And it is because of that, that's the structure of the search space of many complex spaces, and because of that, that you can't play the game in this way. Because it's not like everything that leads to an apple is like a little baby apple that just gets more and more apple. That's simply not the way life works. And so that isn't how this is happening. So, and this is something we discovered. So that leaves up with a really big question. Then how the heck is this happening? Because if you think about it, this is happening consistently. We constantly find things like this. People seem to be at ease with this kind of system. But if they can't do it by trying to do it, then what in the world is the process that's actually allowing them to do this? This is a very important question because this doesn't just apply to pick reader. And if you think about this, we want to know how to get people to design all kinds of things or discover things in some large space. What is it that's allowing this kind of discovery to happen on a consistent basis in the system? Okay, so now I want to answer that question. And the way I'm going to answer it to begin this is to just give you a kind of allegory for the answer, which is to look at just one case, which is the car. This car was discovered, and I want to get to why and how it was discovered. And the reason I select this one, and often show this one to people, is because I happen to be the one who discovered the car. So that's why I know exactly what the story is. So I know this story very well. Not only do I know what choices I made, I also know psychologically what was going on in my head. So I'm going to tell you that. So I discovered this car, which, by the way, was a complete shock to me. I did not imagine, when I'm thinking about Gaussians and sigmas, I happen to know what's under the hood, so I know this is like crazy. Like, there's no way you're going to get a car that are a bunch of Gaussians and sigmas. It wouldn't have even occurred to me. So it was certainly not looking for a car. It didn't even occur to me that I could find a car. So what did I do? What I did do was I saw this, which I thought looks like an alien. It looks like an alien face. It kind of looks like ET, actually.
Looks like Kermit.
Okay, Kermit, that's another interpretation. So I thought ET, but it also looks like Kermit. But anyway, someone else had evolved this, so not me. And this other person had published it on this site, and I saw it there, and so I decided to branch from that. And then what I was thinking, why would I do that, is because I was thinking that this looked like a really good kind of seed for lots of alien faces. This is basically entirely reason, but my idea was like, I'll have lots of little baby aliens. But then something started happening. And what started happening was that these eyes started to descend. And this, of course, through random mutation. But there was a moment when I realized, they actually started to look like wheels. And you can see, of course, in hindsight that these are the eyes of the alien. They just descended and became wheels. And so there was like a moment of epiphany, where I just suddenly realized, wow, this is going to get me a car. And then I drove it a little bit more towards that direction, got a nice car like this. And so, this moment that I said epiphany is like a really critical moment. First of all, it's interesting in its own right, just the fact that, there is this switch point where you suddenly realize something's possible. And so it wasn't like I set out to do this, but then eventually I was open to the opportunity, and then eventually the opportunity struck and I was ready to take it. There's also an epiphany in a larger sense that, like, this entire talk, the entire book that we wrote, none of it would exist if it wasn't for this specific thing that happened while I was evolving the car. So the whole paradigm of objective-based search was shattered by that one moment when I experienced this, for me. And the reason was because it just conflicted with everything I'd ever been taught about search algorithms. I'm in artificial intelligence and machine learning, and so we do these things called search algorithms. And search algorithms work by setting an objective and then following a metric of improvement towards that objective. It's called objective optimization. And this is like completely the opposite. The lesson from this is, like, I wouldn't have been able to do this unless I wasn't trying to do this. I couldn't set an objective, but the best way to actually get it to happen was by not trying to do it. Or let me give you actually more concretely what the story is, because it's really weird if you think about it. There's two things that had to fall into place for this all to come true. The first thing is somebody had to do something that I would never have done. And the reason for that is because I wouldn't have evolved that alien face. I didn't evolve the alien face. So somebody had to do something I would never have done. But then number two, I had to not be trying to do what I ultimately did. You know, because if I was trying to evolve a car, I would not have chosen an alien face, because it's not a car. So the one thing I needed is the thing that I wouldn't have taken if I'd been trying to do what I ultimately did. So all of that has to come together. Someone has to be doing something that I would never have done, and then I have to not be trying to do what I ultimately did, and then we get this discovery. And so if you think about that, then that sounds very coincidental. This is like, wow, you know, you won the pick breeder lottery. Like all these coincidences fell into place, and then you got this car. Lucky you. But here's the amazing thing about this story. Like if it was just this one-time thing, and then I would say, yeah, this is super lucky, you know, amazing. But it's almost always the same story. Just about 99% of the discoveries on the site are exactly the same story. In other words, the only way that these discoveries happen is by not trying to have them happen. And that's how you actually make discoveries. And this is an empirical fact, so you know, this could sound like some kind of new age type of philosophy or something, but I'm talking about an experimental result here, so I'm not talking about my opinion. This is just a fact about the system. And so, like for example, I call this the egg with a hat. Looks like an egg with a hat on it. Well, it turns out that somebody branched from the egg with the hat, and that led to the picture. And as usual, there's this kind of hindsight thing where it's like, well, actually, you know, the lid here is kind of related to the hat mathematically, probably. But there's no way that anyone, it's inconceivable that like the person who branched from this, you know, saw this egg with a hat and like, finally I can get a picture, exactly what I need. It's inconceivable. There's no way that happened. And similarly, the person who evolved the egg with the hat was not thinking about pictures either. You know, he wasn't like, oh, well, you know, finally I've got what I need for a picture, so now I'm going to finally publish it and somebody can get a picture. Completely inconceivable. The only way that this happened was that this person was not trying to get a picture. And there's no way this person who found the picture, when they start with the egg with a hat, was possibly thinking about pictures either. So it's always that story. You know, like this dish leads to the skull. The letter G, it looks like a letter G, leads to Jupiter. It's just the same thing over and over. You would never be able to predict these things going forward. It's 100% serendipity. And so, what this means, so to put what it's saying on the bottom, is that the stepping stones almost never resemble the final product. Like these are stepping stones on the road to somewhere, but they don't resemble where they led. In hindsight, we can see a connection, because there is an explanation, but it is a kind of connection you could never make looking forward. And so the moral of that is that you can only find things by not looking for them. So that's the weird outcome of this. Now I just want to drive home a little bit how crazy this is. Because there's more we can show, like to show just really how crazy this principle is. So one thing we could do, which is say, look, we found these things. Like these are just examples of things we found. We found a skull, we found a butterfly. There's no controversy about that. Obviously, they've been discovered, so there they are. We also know how long it took to find them. These are just results that we happen to know. So it took 74 clicks, basically 74 generations to get the skull, 90 to get the butterfly. Which I'm just pointing out since it's incredibly low. Like, I mean, in the world of machine learning today, you know, when you talk about the iterations that it takes to get to the optimum of something in some algorithm, some sophisticated algorithm like deep learning or something, there's millions. You know, we're talking dozens here. This is just peanuts compared to normal computation for finding things. Okay, so basically what that seems to indicate is that these discoveries are easy. Like that's the usual interpretation in machine learning would be, well, it doesn't take a lot of iterations to solve these problems, so it must be easy to solve them. So let's play a game then. Let's make the skull and the butterfly objectives now, so that we try to re-evolve them. And the funny thing about doing this now is that we know that they can be discovered and that they exist in the search space, and that it doesn't even take that long to find them. We know all these facts a priori. So we can't say, oh, well, these may be like insurmountable challenges or something. They obviously are not insurmountable. So let's say we're going to make these targets objectives for an algorithm which is basically exactly the same algorithm in pick breeder, but instead of a human making the picks, it'll be a computer. And what the computer will do is always pick the image from the set that looks the most like the target. Sort of the classic objective optimization. And so we're going to try to re-evolve these images. Okay, so if you believe in objectives, you know, you should believe in this. You know, this should work. This is your way of doing things. But as you can probably anticipate, this is a disaster. You know, so what we're seeing here is every single one of these is a separate run, the best result that was found in the entire run. And by run, what I mean is 30,000 generations of attempt to re-evolve the image. So remember, these were found in dozens. We gave it 30,000 because I mean, this is the era of big computation, so we get it a lot. And still, miserable failure every time. It's just like universal. And so this is a really, really intriguing result, because like what's interesting about this result is that it's kind of almost like a riddle, in the sense that like if this was just regular machine learning, we could say, like imagine this is the way the field of machine learning is today. For some reason, everybody wants to get a skull and a butterfly. Like this is the world's goal, is to get skulls and butterflies. And so there's like this, they are the standard benchmark in the field of machine learning. Okay, and so we all are going to just like run algorithms trying to optimize towards these goals. And then if that was the case, and we didn't know anything about pick breeder, then I take this algorithm and I try to get these results and I fail miserably every single time. Like the conclusion would be completely uncontroversial. We would just say, well, there's something wrong with your algorithm. You know, you got a crappy algorithm here. But what's really amazing about this result is we cannot defer to that excuse. We can't say this is impossible because these were discovered. I mean, that's just completely contradictory. There's nothing hard about discovering these because these were discovered in only several dozen generations. In fact, by the same exact process that we're now blaming for being incompetent. So it cannot be the explanation. Which shows you that often, like, if you think that the process is to blame, it may not be the process that's to blame. What is to blame here is the objective itself. The point is, you can't get these things if they're your objective. You can only get them if you're not the objective. And so algorithms that we might say are extremely weak and really cannot accomplish anything could accomplish amazing things if only we didn't try to tell them what to do. Which is a very strange lesson again. By the way, evolution on Earth is kind of like this too. You know, it's arguable that like if the target or objective had been humans, that we wouldn't have humans. So why do we have all these amazing things on Earth? It's because they're not the target. You get amazing things when you're not trying to get them. So why is the world so bad? I just want to address, like, why is it so hard to reproduce these things? It's because of this thing called deception. Deception is a really simple idea. It just means that it can appear that you're on the wrong path when you're on the right path. That's called deception. Think, you know, you're following the map in the direction that seems to go to your goal, but actually there's a dead end, so now you're stuck. There's another flip side to deception, which is that it can appear that you're on the right path, but you're actually on the wrong path. So you can appear to be on the wrong path, but you're on the right path, or vice versa. And so this is a case, what you're seeing here are actual stepping stones that lead to the skull. These are the actual intermediate steps in certain generations. And what you can see is that they're very deceptive. I mean, nobody would guess here, like, okay, this crescent is, this is what we need. It's going to get to a skull. Doesn't do good on like an image matching comparison. There's a donut. Okay, that's not probably going to lead to a skull. There's a dish. That's probably not going to lead to a skull. So maybe here you might start guessing, you might get faces. I still don't think you'd guess skulls. And so it's like all these steps along the way, these stepping stones are deceptive. And deception is what makes things hard. And there's no escaping deception, because it's almost like the definition of a hard problem. Like, how could you call it hard if it's not deceptive? Like, if you already know what the stepping stones are that lead to your solution, then you already know how to solve the problem. So there's no problem. So every problem is deceptive that has any value whatsoever. And so this is going to constantly come up. So it means that this is basically a universal problem, the problem of objectives. Or actually, what I call it is the objective paradox. The paradox that trying to solve something makes you fail. Now, so one thing we did when we, as we realized this was like a revelation for us, you know, which we noticed from Pick Breeder, which is a very bizarre story, obviously, since Pick Breeder was not created with the purpose of sort of exposing flaws with like the objective philosophy that sort of guides 99% of the way we run our culture. But once we had this kind of realization that there's something wrong with objective-driven search, we said, naturally, as machine learning researchers, we said, well, it would be interesting then to create algorithms that don't have objectives, like that aren't trying to solve the problem. And so what would that mean? Like things that are more in the spirit of Pick Breeder, which are what I would call stepping stone collectors. Like why is Pick Breeder succeeding so well is because every time anyone discovers something, they've created a stepping stone that can lead to something else. The more things people discover, the more things can be discovered. Now, if you feel like, but where are we all going, then you'd be misunderstanding why the process is powerful. The whole point is we're not going anywhere. We're going everywhere. And it is that expanding everywhere that's making it increasingly powerful the more stuff we accumulate. So we said, why can't we make algorithms in that spirit? Not in the spirit of objective optimization, where there's a metric and you measure your progress toward the goal, but in the spirit of the stepping stone collector. And so we created this algorithm called novelty search. And novelty search is a computer algorithm, a machine learning algorithm, which is tasked not with improving the performance of something, but rather with just doing something new. That's all it tries to do. It's very strange and counterintuitive, but basically the algorithm is just saying, you are good if you can do something different from your predecessor. And so this sounds at first like, well, what is it? It's just random or something, but it's not random at all. Because basically what you're saying is that we're going to try to collect novel stuff. And the thing about novel stuff is that it leads to more novel stuff. And it's kind of immune to deception. That's what's so powerful about it. Because if the stepping stones that lead to somewhere interesting don't resemble that interesting thing, then something like novelty search will still follow those stepping stones anyway, because it doesn't care if it's going towards anything. It's just trying to find stuff that's fundamentally different. So this algorithm turned out to solve a number of problems better than if the algorithm was given an objective. So this sort of confirmed these initially really counterintuitive and controversial results in a more concrete practical domain, or many concrete practical domains. At this point, this has been around for several years, so this has been repeated many times. But of course, if you only see the lesson in pick reader, you're skeptical because you're thinking, this can't possibly be like the way the whole world works. But then again, I would argue, well, how could it not work this way? But still, I've only showed you it in pick reader, so you have a right to be skeptical. So now we expand out to many other domains with this sort of general algorithm, and lo and behold, the principle is repeating itself. And this causes a lot of controversy and sort of surprise within the field. Because here's an algorithm that doesn't know what it's trying to do. It has no goal. It's actually doing better at solving problems than algorithms that are trying to solve them. This, of course, is embarrassing. And so, this is just one example. So in this case, we have a biped robot, and this is a really bad biped robot because it doesn't have a torso. And you can imagine you need a torso to balance. So this is rough. Life as a biped like this is rough. Basically, you say, okay, we're going to try to evolve or learn a controller or an algorithm in the simulated physical world that will allow this thing to walk and not fall on its face. So the standard objective optimization approach to this is a common thing to try to do in some areas of machine learning to try to get things to walk. The standard approach would be rewarded for walking farther. So the farther it walks, the more we go down that path further. And so that is what we call here fitness best. And then the other approach, this new approach, is the novelty best. What I'm going to show you is the very best that was produced by both approaches. So on the left is from fitness, and on the right is from novelty. So this is after the runs are done. And so optimized here, this is pick reader world. And you can see that it's just like a dramatic difference in the quality of the gates. And in fact, that fitness guy is not really stable. He falls over. And so this is just one of many such results that have been demonstrated. And every time you see something like this, or people see something like this, it's always the same reaction, wait a second, how can this be possible? It doesn't make any sense. This thing is worse when it was actually optimizing what we want, and this doesn't even know. And the thing to remember whenever you're shocked by something like that is that the answer is always the stepping stones to walking may not look like walking. What do you need to do before you start walking to become a good walker? It's not necessarily that you get better at walking. For example, one thing you probably need to figure out is how to oscillate, this kind of stuff. Well, there's many ways to oscillate and fall on your face. This thing likes that stuff. That's novel. I've never seen anybody do that before. They fell on their face, but we don't care. We're not actually trying to accomplish anything. This does not like it at all. If you're optimizing and you have an opportunity to fall on your face, you're not going to take that opportunity and see where it leads. And so, again, it will explain, if you understand deception, why this kind of phenomenon would occur. Now, I don't want to confuse you to the point of making you think that this is the solution to all our problems, because it is not. There are many problems where this will fail, but in general, because as you can imagine, in a vast space of possibilities, there's no guarantee you're going to find the one thing you want. That's a needle in a giant haystack. There's no guarantee if we reran pick reader that someone's going to find the skull. They'll find something just as interesting, but not necessarily that thing. So this is not the solution to every problem. That would be a really misunderstanding of the lesson here. But the point is that this is not a solution either. This thing probably, if this can't solve it, this also can't solve it. So there is no just deterministic way to make anything possible. Of course, that would be too good to be true. And there's actually theorems against that. There's something called the no free lunch theorem. But the interpretation I have of these kinds of results is more that what it shows is just how completely embarrassing objective optimization is. You should be really embarrassed by stuff like this. You should not be able to get beaten by something that doesn't even know what it's trying to do. And that also, furthermore, that deception is absolutely pathological throughout life. Like, we do not recognize the degree to which we're stifled by deception everywhere we look. And these kinds of results just bring it to the forefront by just showing you how ridiculous things start to look when you're confronting deception. Like, ridiculous in the sense that I'm actually trying to optimize walking and I'm worse than if I don't try to optimize walking. And that is a joke against optimization. So, now, going a little further than that, we were thinking, at first this was a computer science result. Like, this was basically something we were sharing in conferences with other computer scientists and saying, look at the algorithmic implications here. They're big algorithmic implications, very interesting. We started to realize, and I started to realize, because I was giving a lot of talks at the time in those kind of conferences about this, because as you can imagine, it was getting a lot of attention. I started to realize that what people really got interested in talking about was not the algorithmic implications. They were interested in what the implications were for them as people. And this was also sort of a gradual revelation for me, that actually these results are a critique of like all of objective culture, not just about objective algorithms. And so you can see, like, just pushing it farther, like these kinds of implications, which I'm just going to read off the things that I've already said basically, but they're not just about computer science, they're about like everything. So for example, the path to success is through not trying to succeed. And again, I want to remind you that we're just referring back to empirical results here. This is not like a New Age philosophy or a fortune cookie. I'm just telling you what we've observed. So to achieve our highest goals, we must be willing to abandon them. This is literally like the result that we saw. Here's something else. This is actually a caveat. It is in your interest that others do not follow the path that you think is right, because they will lay the stepping stones for your greatest discoveries. That's the person who evolved the alien face before I got the car, right? I mean, if I'd been all about cars, and then that person had been under my somehow supervision, I said, "What are you doing making alien faces? Man, we're working on cars over here." We wouldn't have alien faces or cars in a situation like that. It would be a disaster. So it is in your interest that others do not follow the path that you think is right. And so these implications are not just about computer science. They are about everything we do. And our culture, I think, is completely dominated by objective thinking, from top to bottom. I mean, it's the way governments run, it's the way education runs, it's the way businesses run, it's the way science is funded. I mean, anywhere you go, it is objectively evaluated by some metric that's trying to check if you're moving in the direction you're supposed to be moving, and that is your justification for doing what you think is important in life or in industry or whatever you're doing, is that metric. And this just shows how absolutely flawed that is if we want to live in a world where people innovate. Because we need to be able to digress away from the objective metric to escape deception and accumulate the stepping stones that will lead to places that we may not have been able to anticipate before. So this is the collaboration point. That was the last. I just want to throw a little bit more weight into this because it's just kind of interesting to consider. Like, what it's saying is really, like, when you collaborate with people, you're in danger because you might move towards consensus. This is often what groups try to do, move towards consensus. But the problem with that is that it prunes out the stepping stones. As you move towards consensus, in other words, there are weird things that individuals in the room might do, but if we move towards consensus, we wash away all of that diversity. So we lose the diversity. We get this washout effect, which is a compromise for all, but a preference of none. So none of us get to follow exactly the path we would have taken. All of those unique paths, each one of which may have led to an interesting stepping stone in its own right, are all washed away. And so it's kind of interesting because there's actually empirical results behind this as well. It just so happens that there was a project at the same time as PickReader called Living Image. And it just coincidental that the people who launched it about the same time as PickReader and created it in such a way that was based on consensus. So it was actually had the same encoding, the same artificial encoding under the hood and so forth as PickReader, except that the way that it decides which parent to choose was based on consensus. So what would happen is you'd also see this kind of palette of options, and people would come in online and vote on which option was the best, and then after like a week, they would just aggregate all the votes and choose the one that got the most votes. So this is a consensus-driven framework based on the most people have to agree on something. And again, I would point out this is the way many organizations are run. And sort of like the National Science Foundation, for example, how does it decide where to allocate money, like what projects? Based on the consensus of a panel. Like the more people agree, the more money that thing is likely to get. So this is basically how we run our culture. And so what's interesting about it is that this thing you're looking at here are the top 9 images that were discovered in the entire project, and that is after 25,000 votes were cast. So a huge amount of human effort was put in. Remember, the skull is like 72 votes. Like that. This thing is 25,000. This is the best stuff that they got. And the only difference is that this is based on divergence. So basically, people are left alone to follow their own paths. That's a key aspect of Big Food. Remember, I branched and I'm left alone. Nobody can tell me, oh, no, you need to justify why you're doing that. I do my own thing. And this is based on whether people agree. And so, my question is, which world would you rather live in? Because that is basically our world. This is how we run things. So it's pretty interesting. What would it be like if we ran things more like this? The reason we don't do that is because we are afraid. It's basically that objectives are a security blanket. They make us feel better. Like if I told you, well, I'm just going to do what I find interesting, you would be like, well, hold on a second, like where's your justification? Like I'm not going to pay you to just do what's interesting. Give me an objective, show me some metrics. Like I need to justify what you're doing. But that is just a security blanket because many interesting things are deceptive. And so all you're doing is making yourself feel better because obviously we're not going to get to stuff like this, like that, as I've demonstrated throughout this talk. So really, if you want to live in a world that's more like this, which I'm not claiming everything should be like. I'm claiming when we're trying to aim for innovation and discovery, it should be like this. If you want to do that kind of a thing, then you're going to have to let go of your security blanket. So now I'm just going to tie this up sort of and conclude. So what I'm saying here is basically that search processes that do not have objectives, I call them, another word I like to call them is treasure hunters. It's like there's all these treasures hidden out in the search space. And I don't really care which treasure is which. I just want to find as many treasures as I can. So I'm just scouring out for all the treasures that exist. And these are things that don't have a final objective. And what we see is that when we look at processes, search processes that do not have final objectives, we see the most powerful creative processes that exist. So, okay, I showed you pick reader novelty search. And we see how pick readers discovering all this diversity. It doesn't have a final objective. It's not like we took everybody on pick reader and said, okay, everybody today we're going to try to get a flower. Bad idea. If you think about everything we're saying, you wouldn't want to do that. Novelty search is an algorithmic example, but then think about, like I said, the things like natural evolution. There's no final objective. That's why it's the most prolifically creative process that we know. Far more creative than, say, any engineer on Earth has ever been. All of life that's ever been created in nature. Got it. Human innovation is another example. In aggregate, all of human innovation, like all the inventions that we've ever made, there's no final goal. It's not like there's this uber invention which everybody is directed towards. Like we're all going to invent a time machine by the year 3000 or something. If we were doing that, it would be terrible. We would have nothing. And yet, look at what human innovation has produced. Again, I'm claiming to you, it's because it has no objective that it has been so prolifically productive over time. The stepping stones that we drop for each other are what are leading to new things without knowing where they go. So these are processes that collect stepping stones. They're not necessarily solutions to particular problems. Like that's the point of it. If you said it has to be a solution to a certain problem, then you won't collect a stepping stone. We're just creating potential. And they're creative because they're divergent. And we like to think convergently. It often goes hand in hand with the idea of an objective, is converging towards the objective. Converge constantly. These are divergent processes, explicitly divergent, all of them. That's why they're so powerful. So we really need to think more about divergence. So why would human innovation be any different? Amazing discoveries are less likely as objectives. Everything is based on stepping stones, including outside of computers. We create things because other people who preceded us created the stepping stones that lead to them. Vacuum tubes were created before computers. The people who invented vacuum tubes were not thinking about computers. That's a fact. If they had been, they wouldn't have made vacuum tubes. Then we'd have a big problem because we'd have neither. So why do we frame almost every great endeavor in terms of objectives? What is this costing us? And could we behave differently? And I call that the myth of the objective, and it's everywhere. I'm almost at the end here. So this is just an example that why increasing performance isn't always right. For all you know, the step in the technology that will lead to the revolution here, this is like a massive jump in performance, is a step down. And so what can we do, when we live in a world that works this way? Well, you can reward interestingness. And so I've made this point, that basically our fear of subjectivity, because we always want to be objective, is preventing us from rewarding interestingness. And we have to, at some point, grapple with the fact that there are certain things in life for which there is no objective measure. Those are the kinds of things where we're going off into the unknown. You cannot give me an objective measure that can guarantee me that this thing leads to that thing. It's just not known yet. And so when we're in a world like that, at some point we have to be willing to make a subjective judgment and say, look, I'm an experienced person. I've seen many things like this before. I can't prove it to you and I don't have a metric, but we really should go in this direction. And at some point we should allow people to do that. And remember, it all goes back to the perception. That's sort of what explains why the world is this way. Finally, a quote. This is actually an idea that is not completely new. I've just sort of embedded it into computer science. But, people have been saying this for many, many centuries. It's an old ancient Chinese philosopher, a good traveler, has no fixed plans and is not intent on arriving. You can find lots of quotes like that throughout history. So this is all in this book. That's my book, or our book. I did this with my former student, Joe Lehman. And, so if you're interested in more of this, you could certainly go to that book. If you want to justify to others, if you start talking to others about this, they'll think you're crazy. So you got to get rid of objectives in our company. This book can help you. I don't actually care if you buy my book. No, that's not what I'm saying. But the book could be helpful in the sense that this has tons and tons of evidence, but it's beyond what I've just shown you today. So we tried to collect as much preponderance of evidence, not just from computers, but also from society, to kind of build up a case that would be easier to explain why greatness cannot be planned, as the title says. And also, I'd be happy if you would like to email me. I'd be happy to answer any questions there. And that's my website if you want to see more sort of research. Okay, thank you.
Awesome. I can't think of a better way to have kicked off DTO and the idea of like where we're headed with technology than to show something like this and what Kenneth had to show us, because I don't know where we're going. That's the whole point of this whole thing, is for us to discover it as a group and learn from each other, play off of each other's moves and what each other finds and what we share, and those steps will take us to that next level. Thank you, Ken. What we have next is the Generative Design Lab at Autodesk is going to get on with us, and they're going to show us some tools that use some AI-type algorithms to do design. And I think it will play off of what Kenneth was just showing us. So I will dial that up. If you guys want to grab a slice of pizza and get a drink, have a bathroom break, and we will reconvene. Yeah. A lot of people think it's a little off topic. That's the whole idea.
The finance company because you're talking about objective.
Yeah.
So it's like the objective is to make money. So I mean, imagine selling that to a Wall Street bank.
Yeah. But when I want to print, that's a good point. I think that's a very good point.
Or transfer files.
Yeah. You would be. I've spoken to many strange groups.
Yeah.
Even the military.
Well, I mean, objective of wars.
Yeah. So.
How about a
How
about a chess player? I mean,
there are actually interpretations on this in chess. I mean, like if you were playing, if you wanted to beat the world champion in chess, probably the best way to go about that would be to not try to beat the world champion. Because you're doomed if you try to beat the world champion. You're never going to figure it out. It's too hard. You don't know what the stepping stones are that lead to world champion play. And what you should be doing is treating it like a scientific experiment where you just try different things and see what the effects are on them. And then eventually you learn how they work. And then eventually, if you just try to beat them, you fail. So there is an interpretation even there in game playing.
So mutations, they're randomized, I guess in real life, there's radiation, there's kind of different kinds of mutation cells of that, mutations randomized?
Yeah, so the mutations are random, so in the sense that there is no
You're
design
good to
behind
go,
it, it just
myself.
happen randomly. But so that does often make people think, well, how is this organizing, or what's actually not random? The thing to remember is that the non-random element is the choosing. When you choose which one you want, it's completely not random.
Everything else is random.
And the other things are random, and so like there's a name for things like that, they're called stochastic. Combinations of random with non-random are basically stochastic algorithms. So we have stochasticity, basically, we have some random element, which you can think of the fuel of exploration, but we also have non-random elements, which keep it sane. And stochasticity is behind things like in nature, like all kinds of processes that are productive, like evolution, it's a stochastic process. Selection in nature is not completely random, who lives and who dies, but the mutations are completely random. So when you combine those together, you get a process that's in aggregate, not completely random. If it was, then it would make no sense at all. Pure randomness is not a good algorithm. So that is definitely true.
Email it to him.
Sure.
Set up a
Most
random
discoveries are not made by objectives. It's always,
Yeah, I
it
would,
was coincidence. Let's say.
I would-
That were, I would
Yeah,
not
yeah.
choose that word. I watched this week in a movie called Infinity.
Right,
I don't know if you had a chance to see it.
Infinity.
Yeah, it's about an Indian mathematician.
Oh, yeah.
So he was trying to explain how he came up to those
Right.
incredible formulas and patterns he was seeing.
You got Roman Newton.
Right,
Yeah.
exactly. So the way he explained it, it was never like, he was not looking for them. They were
Yeah.
just coming to him when he was in state of meditation
Yeah, yeah.
or dream state
Yeah,
or
yeah.
whatever. So
I mean-
it was not something he was
Yeah.
looking
Yeah, I mean, if that seems weird, there's a Wikipedia page on serendipity, if you look at it, it's
Yeah.
quite weird, because there's all these discoveries that are pure
We're trying to get
serendipity.
connected now, so yours
And-
is down, huh?
The interesting thing about it is, if you look at the people who made the discoveries, they're all educated, they all have a good track record. You'd think if this is pure randomness, it would be just random people making discoveries. But why is it that it's always these really smart people who have accidents?
Yeah.
It's because serendipity is not an accident. That's a misinterpretation of what it really means.
So, give me just a second,
The ability to follow a
email.
path of interestingness
So
is
set
not
up,
something
and you'll
that is independent of intelligence. I mean, it requires intelligence.
Or what are we saying, you have to be open to receive it.
You have to be open to receive it.
Exactly.
Right, yeah.
That's
Exactly.
the other key thing. And there might be other kind of background things that happen that influence that
Right.
openness, or other things that are kind of coming in.
Yeah, completely. And, I mean, there's many people who will point to certain impressive objective-based endeavors, like, for example, the Wright brothers designed the plane. So then they'll say, well, what about that? What do you explain? And I explain that by saying, look, that's just the tail end of a very long chain of discoveries. Almost every one of those had nothing to do with the Wright brothers. They just went from that last stepping stone to the next step. So they don't get credit for the engines, the engines and so forth, and what led to the engine, and the spark plug, and you can go back. And so, we tell these stories that are very objective, kind of heroic stories, like this guy, this visionary, just said, I'm gonna make this. But it's always situated in history at a very convenient time. We couldn't have created the space program in the 1860s. It was in the 1960s because the stepping stones didn't make. So when you're a stepping stone away, you can make an objective. It's just like when I realized I'm getting close to a car. Then I can say I'm going to get a car because I realize I'm getting close.
Is it?
I think that the genius is to realize you're getting close. And that's when you
What
can
is the
be
chance
visionary.
that somebody else discovered the plane in Brazil, in Rio, they can repeat the plane, before
Oh,
the
yeah,
Wright
yeah.
brothers.
There's a lot of those.
If you
So,
send it,
I mean,
you'll,
what is the chance
your,
they
We're here,
have
hold on a
all those
second.
stepping
Yeah,
stones?
that's,
So if the plan was right,
Yeah,
that's what you basically said.
that's right.
there, don't worry about it. You got Anthony right there.
Derek, who are we connecting to?
Anthony Huck, Director of the Generative Design Lab at Autodesk.
It's funny, I've actually talked to Autodesk about this.
Yeah?
They're aware of this stuff, yeah.
Yeah, they're doing some stuff. Hopefully that's what you can show us.